Hello, everybody, and welcome to the Mechanochemistry discussions. My name is Ashley Martini, and I am the Associate Director of the NSF Center for Mechanical Control of Chemistry, or the CMCC. The goal of Mechanochemistry discussions is to bring our scientific community together, albeit in a virtual way. The seminar series is being presented on YouTube. It will be streamed live on the third Thursday of every month at 10 a.m. Central Time. However, each seminar will be recorded and saved and available on YouTube to watch at any time. The format of the presentations will be 30 minutes plus 10 minutes for Q&A. We already have an excellent series of speakers lined up for 2020, as shown here. And again, these are on the third Thursday of every month. We're working right now on another set of great speakers for 2021. In terms of questions and answers, again, there's 10 minutes at the end of the presentation. Keep in mind that the webinar is being recorded. If you have questions, we encourage you to email them to cmccdiscussions@gmail.com, and we will forward your questions to the speaker. Alternatively, if you have a YouTube or Gmail account, you can post questions directly to the comments section in YouTube. However, note that we reserve the right to remove comments on the YouTube channel if they do not adhere to the CMCC values of inclusion and respect. Before we get started, I'd like to give a great big thanks first to Dr. James Batiste, the director of the CMCC, to Noah Sheehan, who's helping with the logistics of the seminar series, and finally to Jennifer Belsick, who is the administrative coordinator of the CMCC. So thank you so much for joining us in these mechanochemistry discussions. We encourage you to subscribe and follow us on YouTube, as well as following the center more generally on Twitter. So let's jump right into it. Today's speaker, we're honored to have Dr. Adam Braunschweig from the Advanced Science Research Center of CUNY. Dr. Braunschweig received his BA in chemistry from Cornell, PhD from UCLA with Fraser Stoddard, and did postdoctoral work at Northwestern with Chad Merkin. He has held faculty appointments at NYU, University of Miami, and now at Hunter College and the CUNY Advanced Science Research Center, where he's a full professor of chemistry and nanoscience. His awards include an AFOSR Young Investigator Award, the Early Career Award in Physical Organic Chemistry, and a Cobley Fellowship from the National Academy of Sciences. His research interests include synthetic mucus, carbohydrate receptors, solar energy harvesting with self-assembled organic systems, and surface chemistry, including surface mechanochemistry, which is the subject of today's talk. Specifically, Dr. Braunschweig will be presenting today on quantitative studies of bond formation under applied force, the mystery of two pericyclic reactions, and we're very much looking forward to it. Again, thank you for joining us for the CMCC Mechanochemistry discussions.
Thank you, Ashley, and thank you, James, for the invitation. And it's my pleasure to join you for the second CMCC lecture. What I'm going to be talking about today is I'm going to be talking about doing reactions on surfaces to understand how force affects bond formation. And the specific examples that I'm going to be talking about are two pericyclic reactions. I'm going to be talking about the Huisgen reaction and the Diels-Alder reaction. And then afterwards, and more generally, I'm going to be talking about the challenges that we face when studying reactions on surfaces and how to overcome some of these challenges to accelerate our ability to understand and study reactions on surfaces. So the specific focus of this talk is mechanochemistry, and this is my definition. Just to keep it simple, what we're looking at is just how force applied to molecules affects the making and breaking of chemical bonds. Other people have different definitions, but I just want to keep it very focused on force and the making and breaking of chemical bonds. And there's two aspects to that. There's the making and the breaking. But up until this point, the great majority of effort has been devoted to breaking bonds by applying force. And what the community has done is they've developed these molecules called mechanophores. They're specially designed molecules or functional groups that upon the application of force, the bonds rupture controllably and predictably. So examples include these benzene cyclobutanes, these cyclopropanes, spiropyrans, and then these other cyclobutanes that are specially modified to make bond scission easier. And because these are generally considered the weakest bonds in the molecule, they're the most susceptible to force. It's kind of like the concept of the weakest link in a chain. When you pull on it, it's going to come apart. So the point is, generally, the community has focused on breaking chemical bonds. And these really interesting systems can be used in a variety of functional materials. So this has been the focus of research for about a decade now, where people are trying to put controllably breakable molecules within a series of materials. These include, for example, mechanical sensing polymers that have come out of Illinois and Minnesota, soft robots where you can cause mechanophores within a larger matrix to open and close. And here you see the example of somebody picking up a bottle. Invisible inks, and I'll return to this idea later, that's come out of the Craig group at Duke. And then self-healing materials, where when stresses are applied to bonds, they break controllably, and then when the stress is relieved, they can self-heal. So there's been a variety of different really interesting things that have been done with this concept of bond-breaking mechanophores, but there's still many, many open questions. And the big question that really exists in this field from my perspective is, how do we understand these molecules quantitatively and theoretically? How do we understand how force affects chemical bonds to use it predictably? And I'm going to talk about the challenge of quantifying the effect of force on chemical bond breaking, and then more importantly on bond forming. The reason why me personally, my group is so interested in bond forming is because what we're looking for is new, low solvent, low waste methods for forming bonds, low energy, low waste, and that can ideally provide molecules that can't be formed under any method. So there's a lot of opportunities here if we can only understand and predict how to form bonds with force. And then a corollary to that is, if we can then predict which bonds can form, can we understand the stereochemistry and the regiochemistry to really make tailorable synthetic compounds based on force? But to do all of this, it ultimately relates back to this idea where you need a quantitative theoretical understanding of how force will affect bond-forming reactions. So I'm going to talk very briefly about each of these challenges and the state we're in. Right now, quantitative understanding of force on reactions is lacking. And again, the field has been dominated by bond breaking. And this slide is meant to illustrate just what a challenge this is. So generally, the way that force is applied to mechanophores, there's two methods. You can either embed these mechanophores within large polymers, you sonicate them, the shaking solution grabs onto the ends of those polymers and pulls them apart. And then what you can do is you can take those polymers, look at them by GPC, and see the lengths of the chains after they've broken down. The problem with this is there's a lot of bonds in the system, and it's very difficult to quantify the set of cleavage. So any effort to either quantify the force on the polymers or understand where they're breaking is really a dead end. Similarly, you can pull on molecules with atomic force microscopy, but you have the similar convolution of so many different effects attributing or accounting for the changes in force that it's really hard to quantify exactly the force being applied to the bonds and exactly at what force the bonds may rupture. So again, quantifying force has been such a challenge that in fact it's led to a lot of very high profile retractions in the field. The most famous one, and this is a very important example for the rest of the talk, is this work where a group put together two polymers linked by a triazole, the triazole being the mechanophore, and they said this triazole could be ripped apart, and when you sonicated the chains, it fell apart only at the triazole. There's many reasons why that's probably not correct, but this is just another illustration of the difficulty involved in quantifying the effects of force on reactions. Then finally, there's the problem of selectivity. And I'll use this example out of Illinois, which I think really set the field on fire with the potential of mechanochemistry, but also the challenges in mechanochemistry. What the Illinois group did is they sandwiched this benzene cyclobutane, and they attached it to the tip of an atomic force microscope, and they pulled it apart. The reason why this is so interesting is this is a system whose ring opening is dictated by the Woodward-Hoffman rules, which tell us that the ring will open one way if you shine light on it, and it'll open another way when you heat it up. Conrotary under heat, disrotary under light. Those are the predictions of the Woodward-Hoffman rule. But when you pull on it, you violate the Woodward-Hoffman rules and you get selectivity basically dictated by the molecules wanting to be as far away from each other as possible. So what this work revealed is that applying mechanical force to molecules can really lead to molecules and reaction pathways that are different than you might get with force or light. But there are still no general rules that predict what that selectivity is. So what I've been trying to do is give the general landscape of the field, which has focused primarily on bond breaking. But again, what we're interested in is bond forming. And this is really, it's an honor to be invited to give this seminar because I'm sandwiched between the two giants in the field. If you tuned in last time, you heard a talk by Tomislav Frišek at McGill, and next speaker is James Mack at Cincinnati. And what these two groups and these two researchers and the groups have shown is that mechanochemistry can really be used for bond formation. What they do is they generally take these systems called ball mill reactors, which have these ball bearings. You throw in chemicals, shake them around, and the bonds form. The Mack group in particular has taken a real physical organic approach and started to try to quantify these things. So over here, you'll see that the Mack group has looked at stuff like the frequency of shaking against yield. And they've also looked at how product distributions may change. The Frišek group has really explored a broad scope of reactions, but still the one thing missing, the one parameter that we really want to focus in on is how force affects bond formation. And with these particular systems, that one capability still is lacking, and the question remains open. However, one thing this system does show is that these are reactions that ultimately are forming on and between surfaces. So as you shake these reactors, you have these balls smashing together, and then it's at these interfaces that bonds are forming, right? So what we decided to do is start looking at reactions under force at interfaces, at precisely controlled interfaces. And we were looking for a system that could precisely control the forces being applied. And the question we started with was inspired by these series of contradicting papers from the Reinhout group in the Netherlands and the Stoddard group at the time, I want to say UCLA. And what they were examining was the ability to induce the Huisgen reaction under applied force. The Huisgen reaction is the reaction between an alkyne and an azide but in this case, in the absence of copper. In the presence of a copper catalyst, it's known as the quick reaction. And I believe both the MAC and the Pericyclic group looked at this, the quick reaction under force. But what happened here, and what I'm showing you, is in the mid-2000s, the Reinhardt group postulated that you could take a PBS stamp, you could sandwich an alkyne and an azide on a surface, you could push down, and then you could drive the reaction forward. The Stoddard group in 2008 re-examined this, and they said the reaction is dependent on catalytic copper leaching out of your stamps, and this reaction does not work under the conditions we examined. Bart-Jan Ravu, who was the lead on this study, re-examined the system, and he said, no, it does work. So we decided to re-examine this problem. But to re-examine this problem, you need several things, right? So the first thing that you need is you need tools that can, as I said, precisely apply force between the reacting surfaces. The other real challenge here is the analytical methods. What we're talking about here is monolayers on a surface. And first, there's a sensitivity issue, but the other issue is that a lot of the tools that we use to analyze surfaces are inaccessible and boutique. So for example, XPS can be hard to access. A lot of the general techniques can't be applied to surfaces. So generally we have studied bond formation by NMR as organic chemists, but you can't stick a surface very easily into the NMR. So we need accessible, sensitive tools that are surface specific. And then ultimately, one of the challenges is the throughput of these methods. So my group has dedicated a lot of effort to creating tools that can increase the throughput of studying reactions on surfaces. So I'm going to start by telling you about something called polymer pen lithography, which is a high throughput method for modifying surfaces that was developed in the Merkin group. And basically what this involves is arrays composed of elastomer. And then what you do is you coat the tips of these arrays with inks, and then these arrays come and they can deposit ink like a dot matrix printers. So here you see a torch that my group printed, and one of the real advantages of this technique is it mitigates the sensitivity. So what happens is if you were trying to push with a single AFM tip, you'd be modifying a very small surface. So first, that's hard to detect. Well, mainly that's hard to detect, but with this, your arrays can have millions of different pens. So you're printing over large areas, you're printing a lot of molecule, and you can overcome some of that sensitivity issue. So like I said, the way this works is like a dot matrix printer. You come in with arrays, you mount them onto an atomic force microscope, and then it just comes down and leaves the pattern behind that's controlled by a computer that moves the tips up and down. And the other advantage of this is compared to an AFM tip, the cost is negligible and the fabrication is easy. So what you do is you basically create a master. So what you do is you create an array of holes within a silicone wafer. Then what you do is you do an anisotropic etch that will etch the 100 plane faster than the 111. So if you take this 100 wafer, you have these self-terminating pyramids. You can pour in your elastomer, you cure it, and you stick it onto a scanner, and you can reuse this master over and over and over, negating some of the costs of AFM tips. And here's where it becomes particularly useful in the context of mechanochemistry. You can really control the feature size of the spots that you're making, either by varying the dwell time, because these tips act like leaky pens. So the longer the tip remains on the surface, the more ink is able to diffuse on the surface. But in addition, what you can do is you can extend the Z piezo further and squash that elastomer into the surface. And the size of the features that you get is directly related to the force between the tip and the surface. So you can actually use the size of the feature to determine the force exerted between the tip and the surface. So here you have a quantitative measure of force being exerted on the surface. And these are just equations kind of modeling exactly how much force there is. And it's based on factors like the number of pens, the elastic modulus of the tip, the Poisson's ratio of the material. You take all of those together and you have an equation that gives you the force as it relates to the feature size on the surface. All right, so that's how we apply the tool that gives precise force on the surface. The other thing that we've thought a lot about is how to detect bond forming on surfaces while avoiding these boutique techniques. And here what we did was we decided the best way to do this was make fluorescent inks and redox active inks. Our goal was to print sugars on the surface initially, which is why you see a sugar-based ink. But the way this works is you take your tips, you put some ink on the surface, you deposit your ink on an appropriately functionalized surface. So our inks have alkynes, we deposit them on azide surfaces, we let them react, and we rinse. So what you see here is the large area over which we're patterning. And if you zoom in on one of these patterns, you see we can print a lot of dots and that the feature size can be precisely controlled. But how do we know that we formed a new bond? So this fluorescent intensity map on the right corresponds to this line here. And what this is intended to show is that regardless of the feature diameter, the fluorescence intensity is always the same. And that's because you have a monolayer. So you don't have things growing up, you just have a single layer. So fluorescence can be used to confirm the formation of bonds on the surface when you do the appropriate controls, of course. The other really powerful tool for characterizing bond formation on surfaces in our lab is electrochemistry. So this is an example of how we use the data and use the parallelization enabled by the tip arrays that have thousands and thousands of different pens. So here what you see is we take a thiol-coated surface, we put an azide on a fluorophore, and then in this case, in this particular example, we did use copper to immobilize these on the surface. And this AFM image here shows an array printed by a single pen. So although the feature sizes have a diameter of about 200 nanometers, we're printing 400 spots with each pen. So a significant area of the surface is covered and you get a strong enough signal to detect by electrochemistry. And electrochemistry is incredibly revealing. So here you have the CV, cyclic voltammogram of this gold-covered surface. And the first thing you see is the position of the peaks tell us that ferrocene is on the surface. You can then integrate these peaks, and the integration of the peaks tells you how many electrons came out, and you can use this equation here to calculate the surface density. So the surface density is related to the charge out, the number of electrons per molecule in the covered area. From that, we can calculate precisely the surface density, which is kind of like the surface analogy of the reaction yield. So between fluorescence and CV, we now have very powerful tools when we take appropriately functionalized molecules to detect bond formation on the surface. And then furthermore, what you can do is you can make this log-log plot. And if this line has a slope of 1, that's further confirmation that your molecules are on the surface because they're not diffusing off. All right, now back to this particular problem here. How did we apply those tools that I just told you about to resolve this problem and determine how force actually affected this reaction. So what we did was, again, we returned to these fluorescent inks and these redox active inks. We coated our tips with them. We pushed them into a surface, and then we looked at what came out. The first tool that we used was fluorescence. Here, what you see is each tip printed 6 different features at 6 different times. So here you have the 6 different forces at 60 seconds, 2 minutes, 5 minutes, et cetera, et cetera. And then we washed the surface and we looked at the fluorescence. And what you see here is that fluorescence increases with both reaction time and applied force. The problem, however, or the challenge, is that fluorescence is only pseudo-quantitative, and it can't tell you exactly how many molecules are on the surface. So we went back and we repeated this with our redox active ink. And down here, you see the surface density as a function of both time and force. And this graph right here already explains a previous discrepancy in the literature. So what you see is that our reaction yields, or our surface density, increases with both time and force. And if you think of the work of both Stoddard and Reinhout, if you're not controlling for both factors, there's not going to be reproducibility between the groups, but since they couldn't control force, it's hard to compare the data. There's a third factor that also wasn't considered that I'll get back to. And what we could do with these data here is we could apply pseudo first order kinetics and get a rate constant out. Now, if you plot the natural log of the rate constant versus the applied pressure, and you take the slope of that line, what you get out is this term called the activation volume. The activation volume of reaction is an old term that was adopted when people studied reactions in solution but under applied pressure. And the activation volume can generally be thought of as the difference in the volume between the products and the reactants. When the products are smaller than the reactants, pushing them together drives the reaction forward as a result of Le Chatelier's principle. Okay, so we took this plot, we got an activation volume out of the reaction. However, these old studies included a study of the Huisgen reaction, and the activation volume was known to be about 30 liters per mole, whereas we measured something approximately 5 times or 6 times greater than that. So where's the discrepancy? Why is the activation volume on the surface so much larger than the activation volume in solution? So we made the following postulate or hypothesis. What we did was we imagined that our azides don't act in isolation, but they're tethered to the surface by these chains. And when you push on the azide, you're also pushing on the chains below them. So the observed activation volume is going to be the activation volume of the cycloaddition plus whatever change in volume that you have of the underlying layer. So you have to consider the whole system. So this led us to hypothesize that the activation volume measured is going to be a function of the chain length of the underlying monolayer between the gold and the azide. So what we did was we repeated these experiments with different alkyl chain lengths. And then in collaboration with the Hauck group at UCLA, they computed activation volumes based on the single conversion of a anti-conformation to an eclipse conformation, which would cause the chains to bend. So on the left are our values, and on the right were the computed values. And you see a near perfect match until you get to about C3. And this actually helped confirm what we were thinking. So in silico, in the Hauck group, what they do is they consider perfect monolayers. However, in the self-assembled monolayer community, we know that chain lengths below about C5 no longer ordered together. So in reality, there's no compressibility along the z-axis for C3 in our system, so our values should be lower than the perfect monolayer. But what this work does is not only quantify how force affects the kinetics of reactions, but it also points to another factor that had not been considered, which is the role of the underlying monolayer in governing how reactions on surfaces under applied force work. So based on this, we turned our attention to another cycloaddition reaction in an effort to resolve something that we call the graphene paradox. So the graphene paradox is that graphene is proposed to be useful for a whole number of different things: sensors, scaffolds for biology, a lot of optoelectronic devices. However, to access a lot of that potential, a lot of that potential comes from the stabilizing conjugation, but to access that potential, you have to functionalize it. But functionalization is difficult because graphene is so stable. So we thought, how can we use force-induced pericyclic reactions to functionalize surfaces? And what we did was we found some older work from the Haddon and Hout group, where they looked at graphene flakes in solution, and they saw that these flakes could behave as dienes in a Diels-Alder reaction under some very specific conditions. At 50 degrees, it went forward, but at higher temperatures, it went backwards. And nevertheless, what they did was they proved that graphene flakes at least could act as dienes in the context of 4+2 Diels-Alder reactions. So we thought to ourselves, could we use the same idea, because Diels-Alder reactions are also pericyclic reactions with negative activation volumes. Therefore, this should work here as well. So it's hard to do fluorescence on graphene. So rather than create a fluorescent ink, we created a Raman active ink as well as an electrochemically active ink. And both of these have a diene, cyclopentadiene, that we attach to the ink. Then we would put this ink on our tip, apply a force, and hope for patterning. So this is what the data look like. What you see is we can pattern small features about 5 microns over large centimeter scale areas. And what you see, this is Raman mapping. I think this is the D band, confirming that we get a conversion from sp2 hybridized carbon to sp3 hybridized carbon. That's also what these data show as well. So what you have here is clean graphene, and there's going to be some ratio between the D and the G bands. In our control experiment, what we did was we pushed down on regions of the surface, but in the absence of our diene. So no reaction would occur, and the ratio stays the same. The bonds do not change. In a non-patterned area, the same, but in the patterned area where we exerted force and we have our diene present, what you see is not only an increase in this ratio, but you also see the peaks corresponding to the side 3 bond, or to the Raman die. And the reason why this peak increases in intensity is because this peak is characteristic of the sp3 bonds within graphene. So this was the first confirmation that this does in fact work. And then AFM also showed us it worked. However, the monolayer should only be a few angstroms tall, but our features were several nanometers tall, and this didn't make a lot of sense to us. But so we went back to the Hout group, and they did some calculations for us. And the way we explain this is, even under mechanical force, it's hard to get this first reaction to go because you have to disrupt the stabilizing conjugation of graphene, but you can get it to go. But upon the first Diels-Alder reaction, you get a new carbon-carbon double bond forming right here. That carbon-carbon double bond can then participate in another Diels-Alder reaction, and then the polymerization takes off. So you get, instead of just a single cycloaddition reaction, you get multiple cycloaddition reactions because you have the increased favorability of the reaction plus the force driving that reaction forward. So after the first initiation event occurs, polymerization just takes off as a result of the force being applied to the system. And this technique has since been adopted by quite a few research groups in an effort to pattern surfaces. So we were really happy about that because we didn't really consider ourselves graphene experts at the time. Okay, I'm going to step away from force for the remaining 20 minutes or so of my lecture in an effort to talk about something else. These experiments that we did on the surface were incredibly slow and tedious, and it's hard to imagine applying these sorts of experiments to larger systems and do the sorts of studies necessary to develop rules that really govern chemistry on a surface, whether photochemically induced or mechanically induced or thermally induced. So what we did is we stepped back and we spent some time developing new tools for accelerating discovery on surfaces. The first one I want to tell you about is this system that couples these massively parallel tip arrays with the ability to introduce new inks underneath the tips and change the reaction conditions within a single experiment. And by doing that, what you can do is in a single print, try tens or hundreds of different conditions, ideally, and then what would take, under using current tools, weeks or months, ideally do that work in a single afternoon. So what this involved was we built new microfluidics to change the inks underneath these pens, and here what we have are what are called beam pen tips. So what we do is we take the tips, we coat them in gold, and then we shine light through them so that we can ideally do either photochemical or mechanochemical reactions under the surface. This is what the instrument looks like, but I don't find this picture particularly useful. So we made this cartoon that illustrates how our new printer works. So you have the microfluidics. We have some cameras to monitor what's going on underneath. Then you have these tips, and then you can apply some stimulus, either light or force, to drive reactions on the surface. And here what we're doing, what these different colors show, is either different chemicals under the tip or different conditions. And we're doing this all under the same surface, repeating this experiment thousands of times so we can do statistically significant data sets all in a single print. So what we did for a proof of concept here was we just cooked up 3 different colored inks with an alkene in an effort to capitalize upon Thiol-ene click photochemistry. So you take a thiol bound to a surface, you take an alkene, you shine light in the presence of a photoinitiator, and a new bond forms. And the 3 different colors are used so that we can leverage fluorescence microscopy to confirm that we have different materials on the surface. Before I show you the multiplex printing, I just want to show you this concept of accelerated discovery on the surface, which is, in our view, now the only way to study reactions on surfaces. What this print is we took a single one of our fluorescently labeled alkenes, and we wanted to study different reaction conditions. Here you see we are varying both the reaction time, the irradiation time, the amount of light we shine on the surface, versus the irradiation intensity. And what you see is the yield, which is correlated to fluorescence, increases with irradiation time, but counterintuitively decreases with the radiation intensity. And this just points to the importance of being able to do reactions in parallel, high throughput. Because if this reaction doesn't work, your initial thought as a chemist would be, okay, crank up the light intensity. But what these data are showing us is that's actually going to lead to a failure. only with the ability to try so many different conditions were we able to figure this out quickly. And then in addition, having all those data points, what we could do is we could quantify the kinetics of the surface reaction with just data gathered in a single afternoon. So here, what you see is the fitting of one of our data sets to pseudo second order kinetics. And the other thing I just want to point out is error bars. Each of these histograms, or each of these bars in the histograms, represents approximately 30 different data points. So it's really statistically significant, rigorous data as a result of these new tools. And then here you can see that we can, in fact, put different molecules on the surface in close proximity. We can either serially introduce different colors. So this is the compilation of the 3 different fluorescent channels shown below. You see we could print the blue, the green, and the red. Alternatively, we can capitalize on the microfluidics to mix the compounds in different ratios. So the numbers here correspond to the flow rates in microliters per minute. These were printed with 5 microliters per minute of just the green dye. Here were the different mixtures of green and red, and then here's just red. So there's a variety of different things we can do to introduce now new chemicals into the system. And then just to show the flexibility, we created these 13 color dyes by mixing the inks in different proportions. However, one limitation that we had with this system is every location, every tip is printing the same thing. And ideally, we would want every location on the surface to be able to print something different. So what we did was we built this new printer that incorporates a digital micro mirror device. What that is that's approximately 750,000 different mirrors. So you shine the light on the mirrors and they either direct light to the surface or off the surface, resulting in a pattern with approximately 750,000 different pixels that are computer controlled. So you just upload an image and it prints on the surface. We used our microfluidics to introduce these reactions. And then we initially just wanted to explore whether we could do organic chemistry, photochemically directed light on a surface. And at the end of my presentation, you'll see how we're now trying to use this to do mechanical reactions. But what we did was we first tested atom transfer radical polymerization. The reason why we did that is because it's a very versatile polymerization with broad monomer scope, used for a lot of things. But the other reason why we used it is it's very oxygen and water sensitive. So we reasoned that if we could do this reaction, we could do reactions with any tolerance problems within our system because we encase the whole thing within a air-free chamber, right? So the point is we picked ATRP because it's picky. Now, again, this is showing our accelerated optimization of surface reactions. What we wanted to do was create patterns where we could control the brush height very precisely at each position. So the first thing we did here was we printed polymers of different heights of a vinylic monomer with a small amount of fluorescein methacrylate doped in. Then what we did was we took the AFM and we can correlate fluorescence and height. So once we have this correlation, we don't have to do AFM every time, but we could use the fluorescence to determine the height of the polymers. Then what we did was we took this picture of the Statue of Liberty, because we're in New York, and we deconvoluted it into 6 different levels of intensity. We loaded the 6 images into our printer, shine light for a different amount of times, and you can see this beautiful image that was generated where the differences in contrast correlate directly to the differences in polymer height, right? And there's no other way to do this without a series of complicated photomass. And then of course you have resolution issues, but you can do it with photomass if you want. And then here you see the AFM of the eyelid and the lip, just further confirming that we are able to precisely control the heights of the polymers in each of the 750,000 different pixels. So what about controlling both the height and the composition of each polymer? This would be incredibly complicated in any other printer. You would need, what we have here are 3 different polymers and 4 different heights of each polymers. So you could possibly do this using 12 different photomasks, but we could do it in just approximately an hour, and that time is really dictated by the kinetics of the polymerization. But one thing that we managed to do that you can't do with any other printer is the following. Here what we did was we printed block copolymer arrays where the height of the overall polymer and the length of each of the individual blocks within the polymer is also precisely controllable. So here you see a feature of constant height where these numbers correspond to the different growth times. Constant height because here you're decreasing red as you go from right to left and increasing green. Or here what you can do is increase both together. The point is arbitrary patterns but complete chemical control in the system. So now any photochemical reaction you can do in solution, you can do on the surface. And in fact, the exploration of the different reaction conditions occurs much faster because in a single surface in a single afternoon, we can try hundreds of different conditions. That's illustrated here in work done by an undergrad at the time, Alexa Wong. And we were interested in exploring the Thiol-Methacrylate reaction. Here's a reaction popularized by Chris Bowman and Christy Anseth in Colorado, except it hasn't been used at all to functionalize surfaces. And that's because it still remains relatively poorly understood compared to other reactions. But here we said, we can fully explore the roles of all the different reagents and how they affect the growth rate in just a few simple experiments. So here you see Alexa's exploration of the light intensity, the effect of the concentration of TPO, and the concentration of the iridium photocatalyst on growth kinetics, right? And what's really amazing about this slide is she tried over 200 different polymerization conditions to really understand exactly how each of these different parameters affected the grafted from polymerization, right? So what we're really starting to work in is a regime where the discovery and optimization, something that would have taken years to do 200 different conditions, can now happen in the matter of days or weeks, right? And here's just an image that she made. This is our facility at the Advanced Science Research Center. What she did was she took this and she grew it out of fluorescent brush polymers. And right here, she found the CUNY logo. And in fact, you can see it says CUNY right there. Oh, excuse me. Sorry about that. Now, the last thing I want to tell you about before I tie this all back into how we can use this for mechanochemistry are results that I just got early this morning from a student in my group, Yurjan Zoldasov. And what we were interested in was stimuli responsive surfaces to create hidden images. So hidden images, it's an art called steganography that dates back all the way to the ancient Greeks. And the way that we sought to accomplish this was by creating films composed of a non-responsive polymer and a temperature responsive polymer that we would pattern side by side. So when you initially look at this film, all you see is a flat film, but upon heating above the LCST of the NIPAM, the NIPAM would collapse, revealing a hidden image. So here in the bottom right, what you see are the 2 polymer blocks of identical heights. You have the non-responsive polydimethylacrylamide on the left and the responsive polynipam on the right. And upon heating, you see only the NIPAM collapses. And one thing that he discovered was regardless of polymer height, the ratio, the collapsing ratio stays constant. But the real challenge here is Jurjan had to find conditions under which he could grow brushes of exactly the same height. So to do that, he tried over 400 different polymerization conditions illustrated in these graphs, where for both DMA on the left and NIPAM on the right, he explored the role of monomer concentration. He explored the role of light intensity, monomer concentration, and the concentration of the initiator here. And then he was able to determine how each of these rates, each of these different parameters affected the growth rate. So here, what he did is, out of these 400 different conditions he explored, he chose one condition for NIPAM, one condition for DMA, where under these conditions you could grow polymers of the exact same height. Right, so here you see the first hidden image. So just as an example, he created this cross. And then when you heat this cross that's embedded, the cross is out of NIPAM embedded within DMA. You heat this up, the cross shows up. It turns out that the lower features show up brighter. You can see this cross here. But just to show that we can print over large areas and actually send an important message, he took this QR code and printed it on the surface. And then here you see the image of the QR code, and this GIF right here shows part of the image, this bottom left square that you can't actually see, appearing as you heat up the surface. So we call this a 5-dimensional hypersurface because to define any point on the surface, you need the X and Y coordinate, the Z coordinate, the chemical composition, and the response to temperature. So last week, I thought that was pretty cool. But now we have something much cooler that blows us away that we call the 6-dimensional hypersurface that really builds upon all the chemical capabilities that we've created, the small feature sizes, the precise control of growth, and the ability to create block copolymers as a result of the microfluidics. So what Jurjan did was he took this silicon wafer functionalized with the appropriate initiator, and he printed a first pattern out of NIPAM. On top of that, he grew a dimethylacrylamide non-responsive layer to the same height. He then, on top of that, grew a dimethylacrylamide non-responsive layer with this empty pattern that he then filled in with a fluorophore. Right, so you look at the surface, it looks like a flat surface of polymers. But you shine fluorescent light on it, this tetrahedral carbon shows up. If instead you take the surface and you heat it without any fluorescent light, you get these benzene rings. So here we have a surface with 2 different hidden images that appear, one if you shine fluorescent on it, another if you heat it. And the only way we're able to achieve this is a result of being able to fully explore 400 different printing parameters so that we can control the heights relative to each other very precisely. All right, now back to force. How does all of this relate? So we have the microfluidics, we have the tip arrays. What we need is some way to get the tip arrays to exert force. So right now we're working with our collaborators in Maryland and Boston who have been working on these photo-actuated tip arrays. So now you shine light on these tips and the tips expand, compressing the surface. So you get all of the advantages built into a simple system. But this work is still in progress, and I hope to talk to you about it sometime in the future. Let me just summarize the 3 big accomplishments I think that I told you about were quantitative new models for forces on the surface, a method for patterning the graphene basal plane based on these reactions, and then finally a whole new set of tools that really accelerate our ability to explore surface chemistry, which is the real enabling technology that I think we have to focus on to push the field of surface chemistry forward. That being said, let me acknowledge the people that did this work. This is an older picture of my group, but we can't take group pictures anymore. Let's see, Dan here and Carlos, who is back here, did a lot of the initial polymer chemistry. Yurjan and Alexa, I talked about their work, and Samia and Angelica also made huge contributions to the work I talked about, which I think is spectacular. The Air Force, the NSF, the Army, and I guess the American Chemical Society have also supported this work, for which we are incredibly grateful. So again, Ashley, James, thank you, and thank you to the audience for listening to me.
All right. Thank you very much, Adam. We're a little over time, but we have an opportunity for just a few quick questions. The first one I've received is, using the polymer pens, can you comment on how uniform the tip size is and how this affects estimated contact size?
Yeah, that's a good question. This was studied quantitatively by the Merkin group, and really it depends on how fresh the masters are, but the tip sizes have a diameter of approximately 80 nanometers, and they're pretty uniform because the size of the tips is based on the self-quenching etching process that occurs in the silicon. So that's the size and the uniformity, so it's only small deviations. Now, for the polymer pens, where you have, the beam pens, where you have an aperture, we can control the diameter from about 200 nanometers in diameter to several microns. So it depends. And then when you're exerting force, the size of the feature depends on how hard you push and is unrelated to the actual diameter of the apex of the tip.
Thank you. The next question is somewhat related, and this is, what is the distribution of force across the contact area for each pen?
Oh, okay, that's a really interesting question. So that's something that was also studied quantitatively a long time ago. And there's a slide on this from an old paper I published, where one of the really interesting things about this system is, if you want to apply uniform force across the surface, you want the tips and the surface perfectly aligned. And that's not that challenging, especially when you have cameras on the side to monitor like we've mounted. I say it's not that challenging. My students might disagree, but we can get it done. If, however, you tilted the tips on purpose, then you could, if you find it beneficial, get a non-uniform distribution of force on the surface. So here, you can envision the tips changing the angle, and then as you tilt the pen array, you can see the force decreases as you go from the most compressed to the least compressed tip.
All right, thank you very much. In the interest of time, we'll probably call it there, but audience, if you have additional questions, please send them to cmccdiscussions@gmail.com, and I will forward them to Dr. Braunschweig, and he can get back to you. So again, additional questions are encouraged via email. So finally, Adam, thank you so much for your presentation. And audience, thank you for being here. We look forward to your participation in the next CMCC discussions, which will be next month.